All right, so let's get going on today's class. So what we're going to be doing hopefully soon is I'll be grading your exams. I'm going to upload the corrected graded exams to Canvas, so you'll have that feedback in terms of exactly what you did correct and what you might have done incorrect. And then as soon as we can, we will in class take up the exam at the beginning of one of the upcoming classes, just so that you can see exactly how it was done. Because moving forward, we're going to be using those exact same skills in everything that we are going to be doing for the rest of the semester. All right, so a couple of more skills though that we're going to be developing. Today, we are going to be taking a look at probability, and we are getting very, very close to the point where we're going to be able to do all those kind of interesting, cool things with statistics that psychology uses in order to determine whether or not a treatment is effective or is not effective, in order to determine whether or not a difference exists between two groups or does it not exist. So we're getting to that point where we're going to be able to start taking a look at data that is like what psychologists take a look at in their work. However, we need to paint that fence just a little bit more and develop some final skills so that we can put it all together and begin hypothesis testing. So to kind of keep us focused on the end goal, we're going to introduce this example here. So let's say that you graduate here from IUSB and you start working in educational psychology, and specifically you're working with children who have autism. So here's your classroom right here with these students here. So in this classroom, you have a sample of children who have been diagnosed with autism. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 individuals in your class that you're working with. And let's say that you, based on your psychological training, develop a new treatment, a new educational technique to be used with these particular children. So let's say that you start taking advantage of the interactivity that can be done with iPads and other tablets, and you say to yourself, all right, I'm going to develop this educational intervention, this educational treatment that is based on using this technology to increase the amount of interaction. And you measure their learning outcomes by the end of your treatment period. You measure their learning outcomes by the end of that school year. And let's say that it is just amazing. Their learning outcomes are way higher than what would have been predicted. With this treatment, they learned way more than an average student would have with the old system. So that's wonderful. That's great. But without inferential statistics, without the hypothesis testing, and without the skills that we are working up towards, what will that mean for the real world? Well, what it would mean is that you have now found a technique that will work and does work for these 14 students. And without statistics, that is it. That is where this story ends. So your wonderful technique of using interactive technology, if somebody says, oh, I have some autistic students in my school, do you think maybe your technology will work for us? Without inferential statistics, all you can say is, I don't know. I have no idea. I can tell you for sure it's worked for these 14 individuals, but I have no way of intelligently generalizing beyond that. So without inferential statistics, you could be sitting on this wonderful finding, this wonderful new technique, and it's not going to help any other student, any other child outside of your classroom. So this autistic child in Europe, no help whatsoever for them. These two autistic children in another school in music class, no help from them. This autistic child who is stacking cans, very typical behavior, no help. This autistic child who is not interacting with other individuals, no help for them. Any autistic child in the world would receive absolutely no help, nothing from your study without inferential statistics. So keep that in mind as we're going through. Inferential statistics is what allows psychology to help the people that it helps. Without inferential statistics, psychologists would work for very, very wealthy people who could afford to put us on retainer for the entire, afford to pay our salary to help one specific individual. And we would work with that one individual and improve their lives. And when other people asked us, will that work for my son, for my daughter? We would say, I don't know. Hire me and I can work with your son and daughter, but generalize, no ability to do that. On the other hand, with statistics, we can say that based on this sample of 14 subjects, we can then generalize and say, you know what, based on our results, based on how large and reliable they are, we can say that it worked for these 14 and it will work for the population, the world of autistic children. So this last little step that we're getting towards inferential statistics, never forget that this is what gives psychology its power. This is what allows us to take a look at 14 students in a classroom and make conclusions that'll help the entire population of students. This is what allows us to look at 14 people in a laboratory and make conclusions that will help the world of people out there. This is basically what makes psychology able to do what it does. So keep that in mind as we're working through. We got a few more pieces to the puzzle, and we're going to start today with our introduction to probability. So this introduction to probability is important because statisticians think about probability in a certain way that is very different from a mathematician. So up until now, if you've probably seen probability, you've encountered it in your academic career, it's probably been mathematical probability. And we're going to see that statisticians think about it in a different way. They conceptualize it in a different way. So it's important to understand that difference. And then we're going to take a look at probability and how it's linked to frequency distributions. And that'll be it for today. So kind of like a nice little ease into statistics after last time's exam. All right, introduction to probability. So we'll start off with kind of the mathematical definition first. So for any outcome, the probability of that outcome occurring equals the number of successful outcomes, the possible successful outcomes, divided by all possible outcomes. So this is known as probability. This is also referenced as P. And this is something that we have hopefully seen before. So for example, if you're playing a game and you're flipping a coin, let's say that you need a heads in order to win, right? So that is your possible successful outcome. How many outcomes are successful? Well, there's one outcome that is successful. How many outcomes are there in total? How many possible outcomes? Well, you can flip a head and you can flip a tail. So there's two possible outcomes. 1 divided by 2 is 50%. And that is why we all know that when you flip a coin, it's a 50-50 proposition. We know that when we flip a coin, you got a 50% chance that it's going to come up heads, and you got a 50% chance that it's going to come up tails. So again, that idea of that possible successful outcome, there's only one successful outcome here. Divided by all possible outcomes, there's two possible outcomes. That's where we get that 50%. So probability in stats is symbolized by the letter P. So this should tell you how important it is. It gets its own symbol. And if you ever have heard psychologists talking about their experiments, you might have heard about the almighty p-value and them talking about, how's your experiment going? And they would say, great. Oh my gosh, I tested it yesterday. The p-value was 0.01. And you're like, wow, that's amazing. Yeah, I got my p-value so low. What about your experiment? Not so good. Really? Yeah, I tested it. P-value 0.25. Oh no, that's horrible, right? That p-value is that p-value. It's your probability. So this is the mathematical version of it. But for statisticians, probabilities are equivalent to proportions. So we're going to see exactly what it is a proportion of that statisticians think about probabilities. But we think of it less in terms of fractions less in terms of percents, and we think of it more in terms of portions, parts of a whole, pieces of an entire, area. So probabilities are equivalent to proportions, and we just need a little bit more notation, just in case you see this. If you have a number of different outcomes, so we got outcomes classified as A, B, C, D, all the way to all the different outcomes. The probability of a single outcome occurring is the number of outcomes that are classified as that outcome divided by the total possible number of outcomes. So don't worry too much about that. I just wanted to point out this notation here. If you ever see probability and then in brackets there's something in brackets following it, that's the probability of that occurring. So this is the way of saying the probability of A occurring is the number of outcomes that are classified as A divided by the total number of possible outcomes. So just to give you an example of this, let's say that you're rolling dice. Let's say that you only have the one. Hopefully, if you're dealing with a six-sided dice, you can roll a 1, you can roll a 2, you can roll a 3, you can roll a 4, you can roll a 5, and you can roll a 6. Those are the possible outcomes. Let's say that you're playing a bizarre game and you need to roll odd numbers to win. What are the number of outcomes that are classified as odd? So what is the probability of rolling odd? Well, that equals the number of outcomes that are classified as odd, which is 1, that's odd, 3 is odd, and 5 is odd. We got 3 outcomes. What are the number of possible outcomes? We got 1, 2, 3, 4, 5, 6. 6 outcomes. So the probability of rolling an odd number is, once again, we get that 50%. All right, so that's the mathematical point. Let's get to this idea of proportions. So what are we talking about proportions of? Well, we're talking about proportions of frequency distributions. So frequency distributions are coming back. They are the way that statisticians understand probability. You take the entire frequency distribution, and the probability of anything occurring is the proportion of that frequency distribution that covers that occurrence. So let's take a look at a few examples of this. Let's say that you were interested in studying the outcome of dice rolls. So this was actually something that was done back in the day before they had computers to run endless simulations. So previously, if you wanted to know the probability of something, occurring, what's the probability of rolling a 1 when you're playing with dice? If you got 2 dice, what's the probability of rolling a 7? If you're playing cards, what's the probability of getting 4 of a kind? If you're playing blackjack, what's the probability of getting a 21? Before they had ways of simulating these or the math to accommodate them, oftentimes what they would do is they would just observe massive amounts of these occurrences. So there's a thing called a Monte Carlo experiment because it was named after the statisticians and the researchers that literally went to Monte Carlo casinos and sat there with their pencil and paper and looked at the roulette wheel and said, what just came up? 17? All right. What about now? 12? Okay. Now? 1? Okay. And they would watch dice rolls occur, and they would make notes, and they would watch card games being played, and they would make notes. And there was these Monte Carlo experiments that gave us some of our first information on these very, very complicated probabilities. So let's say that you were doing this, and you were doing a Monte Carlo experiment, and you were at a game where they were rolling a single dice. Right? They were just rolling the 1 dice. You and your team might find out that the times that a 0 occurs would be 0. So if it's a fair game and it's a 6-sided dice, you should never come across somebody that's like, come on, baby needs new shoes, give me a 0, right? That's not going to happen. You might have sat there and seen the number 1 come up 921,541 times. You might have seen 2 come up 1,042,312 times. You would have seen the number 3 come up, the number 4, the number 5, the number 6. And on a 6-sided dice, 7 would never occur. So this is one of the ways that you can figure out the what we're going to use, which is called the expected relative frequencies. So these are the actual frequencies. If you sat there and watched 6 million dice rolls, this is the actual frequency of occurrence of each of these numbers for those 6 million dice rolls. But because these numbers are horrible to use, what statisticians do is they say, all right, well, these are the actual frequencies. But what can we expect? What can we boil this down to? And they basically said, all right, expected frequencies, all of these are basically occurring at a rate of 1 million, right? So that's close. Number 1 occurred close to 1 million. Number 2, slightly over, but still close to 1 million. Number 3, slightly under, but still close to 1 million. All of them were close to 1 million. Let's all just call it equal. They're all 1 million. We'll divide them all by 1 million. So they all occur with a relative frequency of 1. All right, so on another way to think of this, if you roll a dice 6 times, on average, a 1 will come up once, a 2 will come up once, a 3 will come up once, 4, 5, and 6. All of those will come up once. So that's the data we're going to be using, these expected relative frequencies. So now let's take a look at probabilities. Once again, we have the outcomes, and we have the probabilities with which those outcomes occur. And we can see the probability of any dice roll occurring is going to equal the expected relative frequency, i.e., how many times does that thing occur, divided by the total number of occurrences. So for a probability of 0, that occurs 0 times. The total number of occurrences is 0 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 0. That is 6. That gives you a probability, I think it was, oh no, that gives you a probability of 0. Yeah, I can do that one. That one gives you a probability of 0. So 0 will occur with a probability of 0. A 1 occurs once. There's 6 possibilities. That's 1 divided by 6. That gives you a probability of 0.17. Probabilities are usually expressed as a number from 0 to 1. So 0.17 is another way of saying 17%. But in statistics, usually they'll be, again, from 0 to 1. That's why, again, you'll hear those psychologists talking about, what was your p-value? Oh, my p-value was 0.01. What about yours? Oh, no, it was 0.25. They're always from 0 to 1. 0 is it never occurs. 1 is it always occurs. Any number in between indicates the probability. All right, a 2 occurs once. There's one outcome that's classified as a 2. Divided by the 6 possible outcomes, we get a 2 occurring at 17%. And the same thing for 3s, 4s, 5s, and 6s. If you're dealing with an honest, fair dice, all of those will occur with the same probability. And a 7 will occur exactly 0 times. All right, so far so good? This is the mathematical way of thinking about probabilities. This is what we're not going to use. What we're going to use instead is we're going to use proportions of a frequency distribution. So what we're going to do is we're going to take this frequency table, right? Because that's what this is. It's a frequency table. And we're going to change it into a frequency histogram. And this frequency graph is what we're going to use to understand probabilities. This frequency graph is what we're going to use to kind of visualize and figure out probabilities in statistics. So let's take a look at one way that we can use this. Let's say that you were playing a board game. Let's say that you were playing Snakes and Ladders. And you were 2 away from the end, right? So you're 2 spaces away from the end. And you have that rule where if you roll too high, you bounce back, right? So you got to roll exact. If you roll a 5, you got to go 1, 2, and then you go back 1, 2, 3. So let's say that you got to roll exactly a 2 to win Snakes and Ladders. In this case, it's relatively straightforward. You can say, all right, there is 1 occurrence that's going to make me successfully win this game. There's 6 possible occurrences that I could roll. So I have a 17% chance of winning on my next roll. Right? You got a 17% chance that this next roll is going to end the game. That's a mathematical way of figuring it out. statistical way, you would take a look at your frequency distribution here, and you would say, all right, this entire distribution is 100%. The whole distribution is 100% of the distribution. And what part of that distribution is where I win? Well, that blue part is where you win, right? If you roll a 2, you fall into that bar right there. That's the bar that you win. So what proportion is this blue bar of the entire frequency distribution? That blue bar is 17%. So we're going to see techniques for figuring out what that blue bar is. But for right now, it's important to realize that that blue bar, that is the proportion of the frequency distribution where you win. That's the proportion that you're interested in. And very importantly, that proportion is 17% of the entire distribution, meaning that you have a 17% chance of winning on your next roll. So proportions and probabilities are exactly the same thing. And again, it's that proportion of a frequency distribution. All right, so that was a simple example where it really didn't matter, did you use mathematical ideas or did you use proportions? Let's take a look at one where it starts to make a little bit more of a difference. All right, let's say that you were playing a game and instead of rolling a 2, you have to roll an even number in order to win. So a 2, a 4, or a 6 will win you the game. But a 1, a 3, and a 5, you lose the game. So what is the probability that you're going to win the game? Now, in this case, it starts to get a little bit more complicated. Because if we didn't know about the successful outcomes divided by the non-successful outcomes, we might take a look at this and say, all right, I know if there's a 17% chance that I'm going to roll a 2. And there's a 17% chance that I'm going to roll a 4. And there's a 17% chance that I'm going to roll a 6. So those 3 probabilities, what do I do with them? Do I add them all up? Do I take the average of those probabilities? Am I supposed to multiply those probabilities together? What am I supposed to do in this scenario? So there's a number of things that you can do. The correct answer is you add them up. But again, it starts to get a little bit more complicated. Do you add them up? Do you take the average? Do you have to divide something by something? Do you multiply them by 3? Like, what do you do with these probabilities? It starts to get a little bit complicated. That complication goes away when you turn it into a proportion of a frequency distribution. So that entire frequency distribution, the whole thing is 100%. Where is it that you win in this scenario? You win if you roll a 2, you win if you roll a 4, you win if you roll a 6. You win in those 3 blue bars right there. And once you understand that probability is proportions of a frequency distribution, in this case, you can just kind of look at this and say, oh, those blue bars, they're 50% of the entire distribution. Therefore, I got a 50% chance of rolling an even number. I got a 50% chance that on the next roll, I'm going to roll that even number and I'm going to win that game. All right, any questions so far? All righty. Let's take a look at something a little bit more complicated. 2 dice rolls. All right, so let's say that you were playing Monopoly and you're rolling your 2 dice. You got outcomes, you got your expected relative frequencies. Those are your outcomes right there. So there is no ways that you can roll a 1. So if you're playing Monopoly and somebody rolls a 1, they're cheating or they're hiding their dice. There's only one way to roll a 2. You got to roll a 1 on the first dice, 1 on the second die. There are 2 ways to roll a 3. You can either roll a 1 or a 2, 1 and a 2, or you can roll a 2 and a 1. Right? So 2 ways to roll a 3. 3 ways to roll a 4. You can roll a 1 and a 3, a 2 and a 2, or a 3 and a 1. Those are the 3 ways to roll a 4. You can see that the mode here, the one with the highest frequency, is a 7. So a 7 has 6 different ways to roll it. You can roll a 1 and a 6, a 2 and a 5, a 3 and a 4, 4 and a 3, 5 and a 2, and a 6 and a 1. 6 different ways to roll a 7. And then we go all the way down here to double 6s, only 1 way to roll a 12, and no ways to roll a 13. So those are the outcomes, the expected relative frequencies. The probabilities for this, once again, you can figure this out mathematically, So we got no probability of rolling rolling a 1, because there is no outcome that can be classified as a 1. And if you add all these up, there are 36 possible outcomes when you roll 2 dice. There's one way to roll a 2. There's 36 possible outcomes when you roll 2 dice. So there is a 3% chance that you're going to roll snake eyes. So there's only 3 chances in 100 that you're going to land on Park Place, and on your very next turn, you're going to roll snake eyes and land on Boardwalk. All right, the Park Place 1 turn, Boardwalk the next turn move is hard to pull off. And this is why, because there's only one way out of 36 to roll that 2. And you can figure this out for the entire series of outcomes. So once again, one way to roll a 12, 3% chance of rolling, double sixes, no ways to roll a 13. That's the mathematical probability. Or you could take these frequencies, turn them into a frequency distribution, and that's what the frequency distribution looks like. So once again, a statistician will say, all right, this frequency distribution is 100% of the possible outcomes, and that's what we're going to use to understand probabilities. So let's take a look at how this might work. All right, let's say that you were playing a game with a mathematician. The mathematician made this game up, and you needed to roll a prime number in order to win the game. So those are the prime numbers right there. 1 doesn't count, but 2 is divisible only by itself in 1. 3 is divisible only by itself in 1. 5 is divisible only by itself in 1. So we got 7 and we got 11. If you need to roll a prime number using 2 dice, what are the odds? What's the probability that you're going to be successful, that you're going to be able to roll a prime number? Again, it's pretty easy to figure out the individual probabilities, right? 3% chance of rolling a 2, 11% chance of rolling a 5. But what do you do when you have to roll either a 2 or a 3 or a 5 or a 7 or an 11? Do you add them up? Do you multiply? Do you take the average? Do you take the variance? Do you do something else with these numbers? How do you make sense of these numbers to figure out the probability of rolling a prime number? Well, mathematically, it can get confusing, but you change it into a frequency distribution, and you say to yourself, all right, that is 100% of the frequency distribution. That blue area represents the areas that I'm interested in. Those are the prime numbers. That's where I win. And the probability that you are going to win on your on that roll is the proportion of the blue area to the entire frequency distribution. And if you're sitting there thinking to yourself, well, wait a second, how are we going to figure that out? Isn't that just as hard as doing the math to figure out the area of this place? You're right, it is, but we're going to see that something magical is going to happen, and we're not going to have that trouble. All right, but importantly to remember, the proportion of this blue area, which is the outcomes that we're interested in, to the entire frequency distribution is the probability that we're looking for. The probability in this case of rolling those prime numbers. All right, so why is not knowing how to calculate that area going to be an issue? Well, let's take a look at a little extreme case, 5 dice roll outcomes. All right, so if you've ever played Yahtzee, right, this is about the only game I know where you're rolling 5 6-sided dice. You will know that rolling 5 6s on your first chance is really, really rare, because there is only one way to do that, and that is to roll 6 6 6 6 6 6 6 6. There is only one way to roll a 5. You got to roll 1 1 1 1 1. There are 420 ways to roll a 13. You could roll a 1, a 2, a 3, a 4. I'm not going to go them all. But anyways, there's all these different ways to roll all these other totals, right? This is the expected relative frequency for 5 dice roll outcomes. I'm not going to put up the percentages. I'm going to put up the frequency distribution. And the frequency distribution for 5 dice roll outcomes looks like this. And has anybody seen a curve that looks like this ever before? Or if anybody had to describe this curve? Mm-hmm. It's the bell curve. So one of the reasons that we're not worried about figuring out the area for each of these frequency distributions is because we're going to find that due to the nature of what we're working with, due to the nature of how our universe works, many of the frequency distributions that we're going to be interested in, especially once we start taking samples, are turning into these normal distributions, these bell curves, these Gaussian distributions. So one of the reasons why we take samples in our studies, one of the reasons why psychology typically does not do case studies, and usually when you open up an experimental article, you'll read, oh, we tested 60 individuals. You know, we had 420 subjects. We tested 32 eighth graders, right? You'll have a sample of subjects. It's because as soon as you go to a sample that is bigger than one, notice here we got 5 dice rolls. That's basically saying we got 5 subjects. As soon as you go to a sample of subjects, your frequency distribution starts turning into this bell curve. So this is why we're not going to worry about, oh, how do we calculate the area of this? Because as we're going to see, other people have done this for us. But importantly, we don't want to lose the fact that we're still looking at proportions. So if I was playing this game and I was, let's say that we were, if you ever play Yahtzee and you're going for minimum points, right? It's just like one of those variations of the game where instead of trying to score maximum points, you're trying to score minimum points. And if I was going for minimum points, and the last category that I had was that, forget what it's called, that catch-all category, the rent, does anybody know? You know the one where it doesn't have to be, does everybody know Yahtzee? So that I can just clear that. All right, so in Yahtzee, what you have to do is you have to roll certain combinations. So you got one that's like 5 of a kind. And if you roll a 5 of a kind, you add up the points. So if you roll 5 sixes, you get 30 points for 5 of a kind. If you roll 5 ones, worst reason ever. If you roll 5 ones, you get 5 points for 5 of a kind. They'll have 3 of a kind, right? They'll have full house, where you got 3 plus 2 of a kind, right? They'll have a straight, where you got to get them all, 1, 2, 3, 4, 5 in a row, or 2, 3, 4, 5, 6. Okay. Anyways, they have one catch-all where it's just random junk, is what I'm going to call it. And this is one where you don't need any pattern. You can just put points in there, but you only have one of those categories. Let's say that I was playing against someone and I was going for minimum points. And in order for me to win, I had to roll 5 dice and I had to get 12 or less, right? That was how I was going to beat him. I had one spot left. It was this random spot. And in order to win, I had to roll 12 or less. What's the probability that I'm going to win this game? Well, we take a look at here. These are all the possible outcomes. So I could roll a 5, a 6, a 7, an 8, a 9, a 10, an 11, or a 12. Those are the ones that are going to win it for me. So we color that area in blue. And we can see that that is a rather small proportion of the entire frequency distribution, indicating that I'm probably not going to win this. And we're going to see over the next couple of weeks how we can find that exact probability. So I can put a number on this and I can say something like, oh, I only have a 13.5% chance of winning. But for now, again, remember that it's the proportion that we're interested in. That small proportion is where I'm going to win. On the other hand, if I was going for maximum points, maybe I needed 22 or higher. That would be this proportion. Sorry, 23 or higher. That would be that proportion right there. And oftentimes in psychology, we're interested in people at either extremes, of a distribution. So there are ways to figure out what is the proportion of people at extremes of distributions. What's the probability of getting somebody who scores 22 or higher or scores 12 or lower, and those are those blue areas right there. So I alluded to this before. Let me just wrap it, mention it right now. This normal distribution, this bell curve, also known as the Gaussian distribution, this is something that occurs over and over and over and over in our universe, especially if you take a sample. And because of that, because it occurs over and over and over again, people like Gauss, who discovered it, and also Laplace, who is also credited with its discovery, they figured out the mathematics behind it, or they started to figure out the mathematics behind it. And since then, countless statisticians have been working on calculating every portion of this normal distribution, every portion of this normal curve. So we're going to see that instead of us having to calculate this curve, instead of us having to calculate these proportions, we're going to see how we can access their work. Basically, spoiler alert, it's in Appendix 1 of your textbook. We're going to see how we can access their work to figure out what is the exact proportion of that blue area to the entire frequency distribution. And I'll also just kind of allude to why this occurs so very often in our natural world, and especially in psychology, and it has to do with this column over here. As soon as outcomes are based on more than one thing, you get yourself a normal distribution. So the reason that this distribution turned into a bell is because the total in this, the number of the frequency with which things occurred had to do with 5 separate things coming together, right? So when 5 separate things come together to form one total, right? This is 5 dice coming together to form a total of 30. This is 5 dice coming together to form a total of 16. As soon as a number of different things come together to form a total, you get yourself a normal distribution. So in psychology, in experiments, we use samples so that we have 16 people coming together to form one outcome. We got 30 individuals coming together to form one outcome, so one average, one measure of a group. And also this occurs for the population as well, because try to think of any characteristic that a human being has that is determined by one and one thing alone. And you will find out that it is not very much. So if you take a look at something physical like height, height has a number of different components. There's a genetic component to height. People from tall parents tend to be tall. People from shorter parents tend to be shorter. There's a nutritional component to height, right? If you're malnourished, you're not going to be very tall. Doesn't matter what your genetics say. There's a disease component to height. A lot of super tall people are the ones that were able to avoid diseases and hospital stays when they were children. There's an exercise component to height. There's a number of different components to height, and that's why height in our society follows a normal curve, where there's not a lot of super short individuals, not a lot of super tall individuals. Most of us are somewhere around the average. We have this normal distribution right here. Another one that you're probably familiar with, one of the more famous ones, is IQ. IQ is something that is on a normal distribution. Not a lot of geniuses in the world, not a lot of people with extremely low IQs, and this is something that occurs because your IQ is not determined by one factor. Your IQ is determined by a multitude of factors. So you have genetics. There's a genetic component to intelligence. You have, again, nutrition. There's a nutritional component to intelligence. You have access to schools. There's that component. You have parental interest is another component of intelligence. You have access to tutors. You have ability to to study. There's a number of different things. You have levels of attention. You have speed of processing. There's a number of different things that occur that determine your intelligence, and that's why it comes on a normal curve. Because the people who are geniuses, right? When you take a look at the Neil deGrasse Tysons, and you take a look at the Bill Gates, and the massive geniuses, they are the ones who basically rolled sixes on every component of intelligence. So, did they have opportunities to go to good schools? Yes, they did. Did they have interested parents? Yes, they did. Did they have the genetics? Yes, they did. Did they have good nutrition? Yes, they did. And they rolled sixes and ended up all the way over here. Most of us that have average intelligence, you got part of some and part of the other. Maybe you got the genetics, but your parents just weren't that interested in you pursuing an education. Maybe you had the parents, but the school district that you were in was just not a good school district. Certain things lined up, certain things didn't. You rolled some sixes, but you rolled some ones, and you ended up somewhere in the middle. So that's another reason why this graph comes over and over and over again, and we're going to spend a lot of time on it, is because especially in psychology, when we're looking at measuring people on different dimensions in order to study behavior, it is extremely rare that any characteristic of a human being is determined by one and only one thing. There are certain occurrences, there are certain things, but most of the things that we're interested in is a multitude of factors coming together to form this one outcome. So that's another reason why we're going to be looking at this normal curve over and over and over again. All right, any questions on that? Okay, so we're going to have a little bit of a shorter day today. Again, just kind of trying to ease into this current section after exam number 1. So just kind of let you know, there was nothing I don't believe was due today, but don't forget about the 100% for your pretest points. Use the Quiz Me option. You're looking for those mastery points. And anything that we're going to be covering, for example, Chapter 4, Chapter 6, those pretest points, they are due by exam 2. So you don't need to do them directly after. Basically, get that practice in prior to exam number 2, and that will earn you 100% on those pretest points. Other than that, that is it for what I wanted to cover today. So probably most of you might call it an early day, but I will be here until the end of class. If you want to call me over, if you have any questions about anything that we've seen today, anything that we saw on the exam or stuff like that, call me over, let me know. Other than that, if you're all statsed out and you want to start Valentine's Day a little bit early, feel free. But if you have any questions, call me over and I'll help you out.